Hello, welcome to chapters 5 and 14 of our Intro Chemistry course. I'm going to walk through this sequence of slides in two separate videos, one to cover chemical reactions and the next to cover redox. So let's get started. A chemical reaction is a process that chemically converts one substance or set of substances into another set of substances. We call our starting material or starting materials reactants, and we call a new set of substances or a new substance products. We always depict the transformation of reactants to products using an arrow that points in the direction of new stuff that's made. So reactants become products. It's through this arrow that all the magic of a chemical reaction happens. Evidence that a transformation has occurred could include a change in color from our reactants or starting materials to our products or final materials, emission of light or the formation of a solid from mixing solutions together. We call that type of solid a precipitate. We could form a gas when we mix things together. There could be a noticeable change in temperature or even combustion associated with the transformation of reactants into products, to name a few. This is not an exhaustive list, but gives us an idea of some of the common ways that we might experience a chemical transformation. In a chemical reaction, we write an equation that describes explicitly what our reactant or reactants are, what our product or products are, and how many reactants and how many products it's going to take in order to make a balanced equation. Just like making a recipe for a particular final product, a chemical reaction sets out a recipe and all of the quantities of ingredients and final materials that will be prepared once a chemical transformation has happened. In order to correctly write a chemical equation, we need a balanced reaction. A balanced chemical reaction will show us the same total quantity of every type of element on both sides of a reaction arrow, so that we never create nor destroy mass in accordance with the law of conservation of mass. For example, suppose that we were going to react aluminum metal with iron 3 oxide to form the new chemical products, aluminum oxide and molten iron metal. This is a thermite reaction, and we're going to describe it using a balanced chemical equation. The first step towards writing a balanced equation is to write out all of our substances as both reactants and products. Remember that reactants chemically transform into products. Reactants are our starting material or materials, and products are our end material or materials. Our starting materials include aluminum and iron 3 oxide that later will get chemically transformed into new things. Aluminum is just the element aluminum. This reacts with iron 3 oxide. We describe more than one reactant by writing a plus sign in between any separate, distinct reactants. Aluminum reacts with iron 3 oxide. We know how to write down a chemical formula for iron 3 oxide. Iron 3 must have a 3 plus charge. Oxide has a 2 minus charge. To write down the correct chemical formula for iron 3 oxide requires 2 irons for every 3 oxides. Aluminum reacts with iron 3 oxide is depicted by this set of reactants. Now, this reaction forms aluminum oxide and molten iron metal, two new substances that must be products of this reaction. So we'll depict that these things chemically transform with a reaction arrow, and we'll write products formulas in the same way that we wrote reactants formulas. Our first product mentioned in this example above is aluminum oxide. Aluminum has a 3+ charge. Oxide has a 2- charge. To balance charges, we need 2 aluminums for every 3 oxides. Lastly, molten iron metal is formed, Fe. This is our chemical reaction. But notice that in this chemical reaction, as it stands right now, there are 2 irons in iron 3 oxide on our reactant side, but there's only 1 iron on our product side at this time. In order to compensate for these differences, we need to also balance chemical reactions. A balanced chemical reaction will be a recipe that shows us precisely how many of each element there are on every one side of a reaction. And what's more is that every side of a reaction arrow must have the same elements and the same number of each type of element. To balance a chemical reaction, I'm going to come up with a list of all of the elements of each type that are present on the reactant and product side. According to the law of conservation of mass, we can't have an element on one side of a reaction and not on another. So, firstly, we've got aluminum on the reactant side. Secondly, iron. And lastly, oxygen. 3 different types of elements on the reactant side. We'd better have 3 different types of elements on the product side, and they'd better match aluminum, iron, and oxygen. And sure enough, aluminum, iron, and oxygen are the 3 and only 3 elements that are found on the product side of this reaction arrow. In order to balance this reaction, what we're going to do next is count how many of each type of element are present on each side of our reaction arrow. On the reactant side, we only see aluminum in the elemental form. There is only 1 aluminum atom on the reactant side. In the compound iron 3 oxide, there are 2 irons and 3 oxygens. Now we'll do the same thing for the product side. In the compound aluminum oxide, there are 2 aluminums, 3 oxygens. In the element iron, there's only 1 atom of Fe. Our last step here is going to be making it so that each one of these atoms, aluminum, iron, and oxygen, is present in the same total quantity on each side of the reaction arrow. Notice that on the product side, right now, we have 2 aluminums, whereas on the reactant side, we only have 1. How do we manipulate this reaction to show 2 aluminums on both sides, or the same number of aluminums on both sides? We need to accomplish this by using coefficients. Coefficients are numbers that come before a chemical symbol or formula and indicate how many of that element or compound are required or produced for a chemical reaction. In this case, the coefficient in front of aluminum on the left-hand side, the reactant side of this reaction, ought to be 2. In other words, we need 2 aluminum atoms in order to make this reaction happen. A coefficient immediately changes everything about the formula in which it's in front. 2 aluminum atoms change our count immediately for aluminums on our reactant side. We now have 2 aluminums rather than 1. This matches up nicely with the aluminum count on our product side. So aluminums, we say, are balanced. Notice that we have to do something similar for iron, except we have 2 irons on the reactant side, but only 1 on the product side. we need a coefficient in front of the iron atom on the product side of 2 in order to balance it. As soon as we place a coefficient of 2 in front of iron, the count of irons immediately changes on the product side. Now we have 2 irons on the product side, matching up with 2 irons on the reactant side, and we say that iron is balanced. Notice that we don't have to modify anything about oxygen because there are 3 oxygens on both sides of this reaction arrow. Oxygen is already balanced. As a few further examples of balancing reactions, I'd like to talk about the first couple from this balancing equations worksheet. Here in this reaction, sodium phosphate reacts with potassium hydroxide to form sodium hydroxide and potassium phosphate. Making a list of all of the elements on every side of the reaction would require us to think about sodium, phosphorus, oxygen, potassium, oxygen again, and hydrogen on both sides of our reaction arrow. But what I'm going to show you here is a shortcut to thinking about clustering polyatomic ions together that can be helpful in balancing equations more quickly. When we recognize a polyatomic ion like phosphate PO4 or hydroxide OH that do not change form from one side of a reaction to another, we can simply count the clusters of atoms as a whole rather than individual atoms that make up a polyatomic ion. For example, on the reactant side of this reaction, we've got sodiums, we've got phosphate ions, we've got potassium, and we've got hydroxide ions. And we have the same types of ions on our product side: sodiums, hydroxides, potassiums, and phosphates. I'll write them in the same order as I wrote them on the reactant side. And now what I want to do is count up how many of each ion are present in this reaction. On the reactant side, we have sodium phosphate, which contains 3 sodiums. We have 1 cluster of phosphate, we have 1 potassium, and we have 1 hydroxide ion before balancing. On the product side, we have 1 sodium, 1 cluster of phosphate, 3 potassiums, and 1 hydroxide before balancing. Placing a coefficient of 3 in front of potassium hydroxide and in front of sodium hydroxide changes the counts of potassium and hydroxide on the left-hand side to 3 each, because a coefficient affects everything about the chemical formula it's in front of. Placing a coefficient in front of sodium hydroxide changes the count of sodium and hydroxide each to 3, giving us a balance in reactants and products on both sides of our chemical reaction. Next, let's try a reaction that isn't already balanced. In the reaction of magnesium fluoride plus lithium carbonate to make magnesium carbonate and lithium fluoride, we'll make a list of all of the ions that we've got. We have magnesiums, fluorine, lithium, and carbonate. On the product side, we also have magnesium, we also have fluoride, we also have lithium and carbonate. So I can use the trick of counting polyatomic ions here, just like in the previous example. We see that in magnesium fluoride, there is just 1 magnesium cation, but there are 2 fluoride anions. In lithium carbonate, there are 2 lithium cations. There's only 1 cluster of carbonate. On the product side, in magnesium carbonate, there is 1 magnesium cation. There is 1 cluster of carbonate. In lithium fluoride, there is 1 lithium, and there is 1 fluoride. Our job is going to be balancing the fluorine atoms and the lithium atoms in this reaction. We have 2 fluorines on the left-hand side, but only 1 on the right-hand side. Maybe my first approach will be to place a coefficient of 2 in front of the formula that contains fluoride on the right-hand side of my chemical reaction. This changes the count immediately for everything in that chemical formula. It changes the number of fluorines to 2 and the number of lithium atoms to 2. And just like that, we have balanced our chemical reaction. Note that if we don't explicitly place a coefficient in front of a chemical formula, that in all cases 1 is implied, and you never have to write a 1 explicitly, although it's not wrong if you do so. I'd like you to try to practice with the rest of these equations, balancing them appropriately using coefficients in front of chemical formulas in order to maintain the same number of each type of atom on both sides of our chemical equation. To help you out, I've given you a list that's an answer key to these problems available on your course Moodle page. So now that we know something about writing out chemical reactions, identifying reactants and products, and balancing a chemical reaction, I'd like to talk a little bit about classifying chemical reactions under broad categories. These are not exhaustive lists of the categories of chemical reactions, but they're the most common for us and the ones that we ought to be familiar with right now. Generally, we can classify reactions as redox reactions or non-redox reactions, and we'll talk a little bit later in the next video about what redox means. By and large, decomposition, combination, single displacement, and combustion reactions are often examples of redox reactions. Again, it's not important that we know what that means right now because we'll talk about it in a little bit. Instead, what we're going to do here is describe how to identify each of these types of reactions. A decomposition reaction is one in which a single reactant decomposes or transforms into 2 or more products. A general formula for a decomposition reaction looks like this. Any old reactant, A, chemically transforms into 2 or more new products, perhaps B and C. The reverse of this process is a combination reaction, where 2 or more reactants get together to form a single product. In a combination reaction, a generic reaction might look like this. 2 reactants, say A plus B, get together to form a singular product, maybe C. In a single displacement reaction, atoms of a single element swap places with an ion in a compound. In a single displacement reaction, we have one standalone substance take the place of a substance that's already in a compound. Perhaps standalone substance, any old atom, A, reacts with a compound formed from 2 or more elements chemically bonded together to take the place of one of the components of that compound. Perhaps A takes B's place in the compound and displaces element B so that it is all by itself as a product. A combustion reaction is the most specific type of reaction that we'll talk about here. For our purposes, combustion is the reaction of a carbon and hydrogen containing compound, something that contains explicitly carbon in some amount, hydrogen in some amount, reacting with molecular oxygen, O2, to form the specific products carbon dioxide and water vapor. So, unlike the rest of the examples of reactions so far, combustion is the only one where we have to look for specific reactants and products. It's not a generalized reaction so much as it is a specific type of reaction of a carbon and hydrogen containing compound. A hydrocarbon reacts with oxygen to form carbon dioxide and water. Lastly, in a double displacement reaction, we have a similar mechanism to the single displacement we saw above, except that in this case, two things will swap. These are sometimes called metathesis reactions. In a double displacement reaction, two partners come to a dance, say partners A and B, and C and D. And A doesn't really like its partner B, vice versa. C doesn't really like its partner D, vice versa. But ions A and D really would like to get together. And ions B and C really would like to get together. These compounds swap partners so that the cation of compound number 1 meets up with the anion of compound number 2, and vice versa. The next 5 slides walk you through specific examples of each one of these types of classifications of chemical reactions. So I will let you peruse them at your leisure, and we'll skip ahead 6 slides from now. So, before we move on to talking about redox reactions, we're going to first explicitly discuss double displacement reactions. Double displacement reactions often take place when we mix two solutions together, each one containing a particular ionic compound dissolved in water. Of these double displacement reactions, there are 3 cases which could lead to evidence of a reaction. These 3 subcategories of double displacement reactions occur when, after mixing solutions together, a solid material forms. We call a solid material a precipitate, and solids forming by mixing aqueous solutions together are examples of precipitation reactions, which are double displacement reactions that form a solid. Alternatively, or in addition, when 2 aqueous solutions are mixed together, a gas might form. A gas-forming reaction is an example of a double displacement reaction. Lastly, when we mix things like acids and bases together to undergo neutralization, this is a double displacement reaction wherein water is formed, and evidence of reaction is given in terms of heat released. We're going to investigate each one of these 3 cases step by step. So the first category that we will investigate under the double displacement reactions, which again occur in solutions when we mix compounds like A and B plus C and D, to have them swap partners to make products, say, AD and BC, are precipitation reactions. What we're going to do is label substances with their corresponding phases. In a double displacement reaction, compounds AB and CD are mixed with water in the aqueous phase. Therefore, they exist as ions floating around in solution. Ions can repartner with other substances to form things that may be themselves soluble or could be insoluble. S in phase designation indicates a solid. We're going to have to learn to identify when an ionic compound will dissolve versus when it will form a precipitate that stays solid in solution. In order to do this, we need solubility rules. In your PowerPoint slides on your Moodle page, this is a live link to solubility rules. I've posted a PDF copy of solubility rules on your course Moodle page, and I'll show you that PDF next. These are solubility rules. I will provide these to you for exam purposes for the rest of the semester. These solubility rules work in a hierarchical order, meaning the things that are topmost on this list apply universally and trump things that are below them on this list. For one thing, anytime an ionic compound is produced from ammonium or group 1A or alkali metal, those ionic compounds must always be soluble. Secondly, generally speaking, all chlorides, bromides, or iodides in ionic compounds render an ionic compound soluble, meaning capable of dissolving in water to make an aqueous phase, except when these halogens are with silver, mercury, or lead, which render a substance insoluble. Soluble means we'll label a substance with the aqueous phase. Insoluble means that we'll label a substance solid. Item number 3 says that chlorates, nitrates, and acetates always make soluble ionic compounds, and I'll let you read down the rest of this list to investigate further. We'll refer back to this list as we move through the next few slides. We're going to write out chemical reactions, and in addition to predicting the nature of substances in our reactants and products as soluble or insoluble, we'll write correct chemical formulas and balance reactions. So, let's do some practice with this. We're going to mix together solutions of various identities to produce products of particular forms. We are going to write out the results of each one of these reactions, giving proper chemical formulas, balanced chemical reactions, and appropriate phases as necessary. In reaction number 1, where sodium chloride, which we're told is aqueous, it must be aqueous because this contains a group 1A alkali metal, sodium, and is therefore soluble, reacts with silver nitrate, AgNO3, which is also soluble because it contains nitrate. According to rule number 3, nitrates are soluble. Produces sodium nitrate, whose chemical formula must come from Na+, NO3-, NaNO3. We just need one of each to make a balanced charge ionic compound. And silver chloride. Silver is Ag+, chloride Cl-. Again, just one of each is necessary to render a chemical formula with balanced ionic charges. So, first steps first, write out chemical formulas for our products. Secondly, balance this reaction. We see that we have 1 sodium on each side, 1 chlorine on each side, 1 silver, and 1 cluster of nitrate. So this is a balanced reaction as it stands. The last thing that we're going to need to do is identify the phases for our substances. Sodium nitrate must be soluble because according to group 1 of our solubility rules, sodium, an alkali earth metal in group 1A of the periodic table, must be soluble. According to rule number 2, chlorides are soluble unless they're in chemical compounds with silver, mercury, or lead. In this substance, silver is present with chloride. We say that when chloride is in a compound with silver, it is insoluble. It must form a precipitate. So we will label this substance solid. For reaction number 2, barium chloride reacts with sulfuric acid, H2SO4, both of which are soluble in solution, to produce barium sulfate and hydrochloric acid. Barium sulfate must have a chemical formula That comes from barium with a 2 plus charge and sulfate with a 2 minus charge. Barium sulfate just needs one barium for every one sulfate. Hydrochloric acid starts with the name hydro, so we know that the anion must not contain oxygen. It must just be chloride. All acids have the cation H+. The correct formula for hydrochloric acid is HCl. Acids we can expect to be aqueous, and what's more is that HCl contains chloride, not with silver, mercury, or lead, so we expect this substance to be soluble in the aqueous phase. Barium sulfate, on the other hand, contains sulfate, which is insoluble with barium. This according to rule number 4 of our solubility rules. Barium sulfate is insoluble, which means that it is solid or precipitate in solution. We need to balance this chemical reaction to finalize things. So we'll notice that we have 2 chlorines in barium chloride, just 1 chlorine on the right-hand side. We need 2 HCl's. We'll notice that we have 2 H's by virtue of placing a coefficient of 2 here, 2 H's on the left-hand side. 1 barium on both sides, 1 cluster of SO4 on both sides, so we are balanced. That's the end of reaction 2. Take a few moments to see if you can write down balanced chemical reactions that show the correct formulas and phases for the next 3 reactions. Pause this video for a few seconds and then I'll come back and show you the results. Here's a balanced chemical reaction for number 3. Here's the balanced reaction for number 4. Keep in mind that mercury 1 is one of the polyatomic ions. It's got 2 mercury atoms with a total charge of 2 plus. And lastly, here's the final reaction, sodium hydroxide reacting with iron 3 chloride. Again, remember that when we write multiples of polyatomic ions in chemical formulas, we'll place them in parentheses. If we don't need multiples of them, we don't have to place them in parentheses. A second subcategory of double displacement reactions occur from gas-forming products, so-called unstable products, shown in these bullet points here. If ever we see the products H2CO3, H2SO3, or NH4OH, we'll replace them immediately with water and a gas. So in addition to looking at our solubility rules, we'll also be needing to keep an eye on these potential products: carbonic acid, sulfurous acid, and ammonium hydroxide. In the reaction between sulfuric acid and magnesium carbonate to make magnesium sulfate and carbonic acid, we form one of those key substances. We're also going to need to keep in mind the fact that we need to check for precipitates using solubility rules, in addition to keeping an eye on these gas-forming unstable products. Sulfuric acid must contain oxygen. We'll use adic-itis to help us identify which substance it is that contains oxygen. In this case, change the ending ic to ate. Sulfate must produce the anion for sulfuric acid. Acids always have H+ in their chemical formula. In magnesium carbonate, our cation is magnesium 2+. Carbonate is the polyatomic anion CO3 2-. Magnesium sulfate, again, has the cation Mg2+, anion sulfate SO4 2-. Carbonic acid, again, because it doesn't start with hydro, must be an oxygen-containing acid. Carbonate, again using adic-itis, comes from the CO3 2-, and acids always contain H+. This reaction can be written as follows. Sulfuric acid must be H2SO4. We need 2 H's for every sulfate. Acids are in the aqueous phase. Magnesium carbonate just needs 1 magnesium for every 1 carbonate. Carbonates are insoluble in water, but soluble in acid, so we should still expect a reaction. This reaction will produce magnesium sulfate, MgSO4, which itself is soluble, according to rule number 4 of your solubility rules, and carbonic acid, which must have the form H2CO3. It's an acid, so it's ostensibly soluble. But what we'll recognize is that H2CO3 in the aqueous phase is one of 3 usual suspects. As soon as we see it, we're going to cross it out and replace it with 2 new substances, water and a gas. H2O, which is liquid, L, and whatever's left over, a carbon and 2 more oxygens, CO2, which is a gas, G. The real products of this reaction are magnesium sulfate, water, and carbon dioxide gas. To balance this reaction, we'll recognize that we've got 1 sulfate cluster on both sides, 1 magnesium on both sides, 2 hydrogens, a carbon, 3 oxygens here, but 1, 2, 3 oxygens in substances that are not sulfate. So we are balanced. This is the chemical reaction that proceeds when we mix sulfuric acid with magnesium carbonate. A final subcategory of double displacement reactions occurs when acids and bases are mixed. An acid is a substance that ostensibly has H plus cations in its chemical formula and will generate a pH less than 7 in solution. Bases are substances that can give up hydroxide ions in solution and generate solutions whose pHs are greater than 7. We say that neutral water has a pH right at 7. Mixing acids and bases causes the reversion back to neutral water with pH 7 and is therefore an example of a neutralization reaction. Neutralization reactions always mix an acid and a base to form salt and water. In the example shown here, sodium hydroxide is a base, hydrochloric acid is an acid, like its name suggests, sodium chloride is a salt, an ionic compound, and water is water. The chemical formulas for these substances can be written by identifying cations and anions once again. Sodium is a +1 cation, hydroxide, OH-. Hydrochloric acid has the prefix hydro, therefore must not contain oxygen. H+ is always the cation in an acid. The anion must be Cl-. Let's write our chemical formula here. Sodium hydroxide, NaOH, which must be aqueous according to our solubility rules, reacts with hydrochloric acid, which is aqueous because it's an acid, to form sodium chloride, which is soluble, again according to our solubility rules, is not unstable according to our gas-forming products, and therefore stays intact just like it is, plus water. Every time we see water in a chemical reaction, we'll label it with liquid phase for these double displacement reactions. There is a worksheet on your course Moodle page entitled Predicting Chemical Reactions, and there is a solutions guide to that worksheet as well. I would encourage you to work your way through all of those problems, and we can talk about them when we meet next. Next up, we will discuss redox reactions in a separate video.